Log on, tune in, find out. Another good idea from Cambridge.
Pleasure to introduce Vijay Balasubramanian from UPenn. Yes, I can't remember, it's from Philadelphia. We're going to talk to us about momentum space entanglement and renormalization.
Great, thanks very much for the invitation. So let's see. So indeed, this talk is about momentum space entanglement and renormalization in quantum field theory, and this is work done with Mark van Ramsdonk and his student Michael McDermott. Okay. So as you all know, that in quantum mechanics, a key property that makes quantum mechanics quantum as opposed to classical is entanglement. And the way entanglement works is that you have some system, and let's say I split it into pieces A and B. A I imagine to be some box here, and B is the outside. And let me imagine that I have this system, which overall is in some pure state psi. Then I can construct a reduced density matrix for the physics in the region A by tracing over the region B. Well, I first construct the density matrix psi, and then I trace over the region B, and this is supposed to give me the reduced density matrix for the region A. What that means in practice is that I can compute observables. So if I want an observable OA constructed out of only the degrees of freedom that sit in the region A, then I can compute its expectation value by taking the trace rho A OA, and that gives me everything. Now, a characteristic property of quantum mechanics is that the system A and the system B can be quantumly entangled. And one way of quantifying the amount of entanglement between the regions A and B is by the entanglement entropy, and which, as you all know, is you take this reduced density matrix, which characterizes system A, and you compute the entanglement entropy by taking minus trace rho A log rho A and add it all up. And it's a fact that this is positive if the overall wave function for the system is not a product of the wave function in systems A and systems B. In other words, if they're entangled, you get a non-zero entropy. Now, of course, there are many different ways of splitting up the system. Here I picked sort of a spatial way, A and B. I could pick other kinds of, I can make A to be some other subsystem. I can pick some other basis. I don't have to pick the position basis. I can pick whatever basis I want, split the system into two parts, and compute the entanglement entropy. And you get different kinds of insights by picking different kinds of subsystems to discuss the entanglement entropy of. Now, what I'd like to do is to consider what appears at first to be a seemingly different setting, which is I want to consider the renormalization group, which a priori doesn't seem like it has any relationship to what we're talking about there. Okay? So here's the renormalization group. What do you do in the renormalization group? In the renormalization group, you trace over the UV, over the ultraviolet degrees of freedom, to get an effective IR theory. And let's imagine that we treat this problem of coarse graining a theory, integrating out the UV degrees of freedom, in the language of Wilson. If we are to do that, here's what I might do. Here's momentum space. Here's P, momentum space. I might imagine that I put some cutoff there. This is the region where the momenta are bigger than lambda. This is the region with the momenta less than lambda. And what I might do is I might try to trace over or integrate out the degrees of freedom on the outside. If I draw the picture like that, obviously it looks a lot like that, right? And so you might very well ask yourself the question, why is it when I do renormalization in the sense of Wilson, namely literally trace out the UV degrees of freedom, why don't I wind up with a low energy density matrix, density matrix with an entropy? And certainly this should happen. If the UV and the IR are entangled. We don't normally think about this, certainly in free field theories, because in a free theory, the wave functional as a function, here are all the momentum degrees of freedom, phi of p. This is the field in momentum space, and this is the wave functional. For a free theory, this by the definition of what's a free theory, that's just the kinetic term, this wave functional is going to be Gaussian, and it's going to be a product on something that looks like, a Gaussian in each momentum degree of freedom. That's what makes the theory free. So in this case, obviously, in momentum space, if you like, the wave function factorizes across different momentum shells. So if you were to go through a procedure of tracing over the UV, you're not going to generate a interesting density matrix in the IR. It's going to be like this, like the case where there's no entanglement. But also evidently, if the wave function is not a product over different momentum shells, then what's going to happen is if you somehow trace over the UV, you should somehow generate some sort of infrared density matrix with a entropy, okay? So what I'd like to do today is, I know I'm going to run out of time, and so because I'm going to run out of time, I'm going to tell you the punchline. First of all, what I'm going to do today is I'm going to argue to you that this is true. Anytime you do the Wilsonian renormalization group, the low energy system, effective system that you're describing, is in a density matrix with a non-zero entropy. So I'll prove that to you on general grounds by just constructing, just trying to write out what it means to construct a low energy density matrix and comparing it with the general expression that you would usually write down to do the Wilsonian renormalization group. So I'll try to convince you that this fact is true, that there is a low energy entropy. That raises many questions. Why don't we notice usually, when you're doing calculations in the standard model, you don't worry about some low energy density matrix. And I'll try to explain why and why not in different ways. First of all, I'll try to argue that the usual calculations we do in the Wilsonian renormalization group are actually equivalent to taking traces inside a density matrix, inside a particular density matrix. I'll try to argue that. And then to make everything concrete, I'm just going to do a bunch of examples, 5 to the n theories in d dimensions, just to show you in practical terms, if you wish to calculate this object, what it is. So you might wonder, why should you care about anything like this? So also, as part of giving you the conclusion first, because I know I will run out of time, I'm going to start by discussing why you should care and the various ramifications of the things I'm going to say. We feel that what we've done is basically think about a different approach to renormalization and think about a different approach to understanding entanglement in quantum field theories. And I'd like to tell you some reasons, applications where you should really care. So one is, in general, we usually ignore the question of when you integrate out the UV, we usually ignore the question of what is the infrared state. So usually we're not thinking about this, but obviously, if, for example, I was doing coarse graining in the sense of a lattice, if I was doing condensed matter physics, right? I have a bunch of spins or whatever on lattice sites, and let's suppose a coarse grain into 4 by 4, and then I get 4 effective spins, and a coarse grain some more, and I get 1 more effective spin. Now, obviously, the state can change. Consider, for example, here, let's suppose that every alternate spin was up or down, right? Antiferromagnetic. Then if you were to coarse grain in this scheme, in these kinds of 4 by 4 blocks, obviously the average spin here is 0. Right? So that looks like a different state than this. Right? The state is flowing in some way. And we usually don't talk about the state flowing because we usually don't have to, or the question we're interested in doesn't completely relate to that. So I think so we usually track RG as a flow in the space of couplings. But also it's worth asking, is it in some sense a flow in the space of states? And one of the things that I think we're demonstrating is that it is a flow in space of states, and there's an interesting flow in the sense that you can go from a pure state to a density matrix with some interesting properties. Okay, so that's one reason why you should care, because I think this has some bearing on a general understanding of what the renormalization group is and what it does to the flow of theories.
Your Hilbert space is changing as well.
It is.
You're not so worried about that. It's more pure state to density matrix.
I'm more in this talk. I'm more interested in the pure state to density matrix. But this issue of, for example, is it a flow just in couplings or couplings and VEVs, if you like, is important in trying to understand the relationship in, let's say, equations of motion ADS and, for example, RG flows. There's the usual second-order equations of motion and first-order flows. But really, the key there, as we will discuss maybe sometime later in the talk, is that there's a second bit of the flow, which is the flow of the expectation values. And the flow of expectation values is in some sense related to the flow in the state also. So I think there are deeper issues overall understanding the renormalization group that are implicated. I'm personally interested here in just the fact that there should be a density matrix. Okay? So a second set of issues that's that I might raise is, given what I am going to tell you, or I hope what you've already told you, but what I'll try to convince you, is why don't we notice the density matrix in the IR that I claim should be there. And so in the end, one way or the other, this has to be about decoupling. This has to arise from decoupling, right? Usually in quantum field theories, the most of the quantum field theories we study have the nice property of decoupling, and we usually mean by decoupling that if I look at the effect of Lagrangian, there's some marginal operators and what have you, and then the effect of Lagrangian looks like some sum of operators, which is divided by 1 over the scale minus, let's say, the dimension of the operator minus 4. Right? So basically, high dimension operators get suppressed in powers of the cutoff scale, and that's what we usually mean by decoupling, namely somehow the high dimension operators go away, we don't have to worry about them. But it's worth asking, what if you don't have UV-IR decoupling in the conventional way? For example, if you think about non-commutative field theories, space-time non-commutative field theories, they don't have conventional UV-IR decoupling. So it's worth asking what the kind of effect that I'm trying to talk about is more important there. One might argue that gravity in general does not have UV-IR decoupling. Here is a crude argument for that, right? So in gravity, the mass of an object is the source of gravity. Now, of course, the total energy or mass takes contributions both from sort of infrared fluctuations and from UV fluctuations. So suppose I had a wave function for some gravitating system which had some support on some very high energy, high momentum fluctuation, right? Then to be self-consistent, the energy in that fluctuation has to manifest itself in the mass of the system, but that's measured at infinity via the ADM mass. Therefore, it must manifest itself in the deep infrared part of the wave function. So of necessity, in gravity, you're not going to get factorization of the wave function between UV and IR. So you might well wonder whether the kind of entropies I'm going to talk about are important in gravity, right? So that's another reason why one should care. And indeed, that's one of my primary motivations. And then there are 2 more reasons to care. One is ADS CMT, namely condensed matter physics. So, one of the big developments in the last few years has been the use of ADS CFT techniques to shed light on interesting ground states in complicated interacting, let's say, electronic systems. Now, a characteristic fact of many such systems, which are undergoing quantum phase transitions, etc., is supposed to be that their ground state wave function has entanglement across many scales. That's supposed to be one of the things that's really hard to handle. That's why it's hard to write down their wave functions, the ground state wave functions of these systems. Well, I'd like to claim that if you have such a setting and you want to do momentum space renormalization, you will generate the kinds of density matrices and entropies I'm talking about. So I think it's practically important for exactly the kind of problem that you actually face in studying strongly correlated electronic systems. And finally, we being a string theory community, there is a relationship between entanglement and geometry that comes about in the ADS-CFT correspondence. So let's see that. So as you know, Takayanagi has proposed that this is the boundary of ADS. If I have this region A and this region B, and I find the minimal surface there, and we're going through the bulk with ending on the boundary of A, then Takayanagi has proposed that the area divided by 4g Newton, let me call this surface n, the area of m divided by 4g Newton, is supposed to be equal to S, the entanglement entropy in the CFT. Now, of course, the entanglement entropy in a field theory, in this kind of thing, where you make a spatial box and you find the entanglement entropy of this box with the rest of the system, in a field theory, that entanglement entropy actually diverges. It diverges because if I have a sharp boundary here, then there are many UV degrees of freedom which pile up and just cross the little boundary. That gives rise to divergence. And in the formula of Takayanagi, beautifully, that's realized as the divergence of this area as you take the edges, the cutoff of this bulk surface and take it to infinity. So that's very nice. Now, the kind of entropies that I'm talking about with cutoffs in momentum space, right, where you put a cutoff in momentum space and you compute the entanglement of the infrared degrees of freedom in momentum space with the UV degrees of freedom, that's not divergent. That's finite. And that's actually nice because it suggests that there is a relationship with this surface area. right? If you want to generate the areas and geometries of surfaces in ADS from some kind of entanglement in the field theory, well, a natural thing to suppose is that, in ADS-CFT, the region outside this cutoff would be the UV of the Q of T. The region inside this cutoff would be the IR of the Q of T. So it would be very natural to hope that some sort of UV-IR entanglement in the quantum field theory would be related in some way to the area of these surfaces. That's very tricky because it's very difficult and complicated to map exactly what renormalization scheme you're using in field theory to particular schemes in gravity. But having said that, clearly a natural thing to imagine is that it's something like a cutoff in momentum space might be, the beginning of a way of thinking about what you want to mean by UV-IR entanglement that generates this area. Yeah, Neil.
Well, just my usual view of quantum field theory, which could certainly be flawed. I mean, you're splitting up the high energy modes from low energy modes. You imagine you have some mass gap, and you're below that mass gap. So don't you know that the state of those massive fields are in their vacuum?
I'm not necessarily thinking about things that have a mass gap. You're thinking about very high, heavy modes, right? You're thinking about very heavy particles and working at scales much less than those heavy particles, that heavy scale. I don't have to think that way at all. Indeed, usually in condensed matter systems, that's not necessarily the way you're thinking. I'm thinking about this in a very general language that Wilson would have used, which is to say, I have a field theory. I'm perfectly free to put a cutoff wherever I want, be it above or below the masses of various particles. And then I'm free to move this cutoff down and see what happens to the theory.
So you're not thinking like the standard model where the cutoff is, I don't know, TeV or 10 TeV or...
I have some general quantum field theory.
Well, the usual perspective of particle physics is that the cutoff is up high.
Yeah.
And we're just stuck below it and that's life.
That's right. And so, in fact, as I will argue, as I will explicitly show later on, taking the example of phi to the n theories, for any theory that enjoys the property of decoupling, it's got to happen that if you're talking about momentum modes far below the cutoff, where you're integrating out, this effect should be small. Specifically, as I will explicitly show, if I have the time, is that if this is a cutoff mu, that the modes that are entangled are largely in sort of a skin, in a sort of power loss skin around this. Yeah. So that a mode that's way down here is not very entangled with that.
And the mode high up,
a mode high up there is not very entangled with that. So it's just a skin here that carries the effect. It's a power loss skin. There's no scale necessarily, right? If there's a mass there in the system, there will be a scale, and then that will affect how this thing falls off. But that's the effect. It's a different, so what we're trying to propose and explain is a different way of characterizing the extent to which different momenta and things decouple. And there's nothing wrong with our current understanding of the decoupling standard. Obviously, it's correct. Well, it's correct. There's nothing wrong with it, right? The statements are true. But what I hope to try to give you by the end is a way of getting more refined understandings of what it means to have different scales talking to each other or not. And certainly it's true in any theory with decoupling that if you're way below whatever the appropriate cutoff is, it shouldn't matter.
Right.
And we will see that.
So I should really be thinking more of CMT, not even ADS.
Yeah, I think in condensed matter physics, for the ground states of strongly, things like quantum phase transitions and everything, this is absolutely relevant. And for me, personally, I'm very interested in this question of how you get geometry out of field theory, and I think it's totally relevant for that. I may not be using today necessarily the right scheme, the right kind of cutoff and scheme to reproduce this area, but it's something like the right cutoff and scheme, because it's something like a momentum cutoff is roughly what. So I care a lot about this, and I care a lot about this. I mentioned the other things as relevant. Okay? Yes?
It looks as if it goes the wrong way, that as you integrate out more, the area of that surface goes down. I know there's ADS warping, but even taking that into account.
So you mean as you go down, the thing goes down? So can we see some examples later? Because it depends, because amongst the factors that matter, there's how many degrees of freedom are involved near the cutoff, and the number of degrees, as you move your cutoff down, the number of degrees of freedom that are near the cutoff that are getting entangled is getting smaller. And also the coupling runs, not in a CFT, but in general a coupling runs. So it's a combination of the running of the coupling and the amount of phase space you have that determines the way this goes. So it's not obvious that which way this should go. Yeah?
So does your entanglement entropy in the momentum space decrease or increase as you lower down the energy scale?
So that depends upon which theory you're talking about. I will talk about phi to the n theories in d dimensions, and I'll give you, you'll see what happens and why it happens. We can explain why it happens. It would be really cool to be able to give, to study theories of interesting flows, right? Phi to the n theories in d dimensions are not particularly interesting in their flows, they're just things that we can do easily. So we'll come back to that. I will certainly not finish this talk, so I'm glad I gave the conclusion first. What time is it, by the way? Is it really 2:20?
Yeah, no, it's 2:25.
Lovely. Okay. So, all right. So what I'm going to try to show you now, I'm going to go through what I claim would be the order of the talk, which is, first of all, I'm going to try to convince you in general that it is a fact that you're going to get that the low energy theory treated in the Wilsonian way is going to have a density matrix which has a finite entropy. So, all right, so I'm going to consider the Wilsonian sort of renormalization group prescription and see what it says for the low energy theory. So I'm going to start with a bare action with a cutoff lambda and a Hamiltonian H, and we'll take the ground state of H to be something psi lambda, okay? So I can write down, of course, a density matrix which looks like psi lambda, psi lambda. I'm going to put this here. So now I'm going to write down the finite temperature density matrix for the system, and you'll see why I'm doing that in a minute. Right? Damn. Okay? Doing that because the zero temperature density matrix is the limit, of course, as t goes to 0 of the finite temperature density matrix. And I'm going to write this in path integral language as 1 over some partition sum times the integral d phi of e to the minus some Euclidean action lambda, where phi at the time minus beta over 2 is equal to, let's say, phi y, and then you have, at late times, you have some phi hat y. This calculates the matrix elements of this density matrix between this configuration and this configuration. Okay? So now I'm going to split the Hilbert space into A and A bar. Okay? So this index y, which indexes field configurations, I'm going to split as A and A bar so that I can write the configurations as phi A times phi A bar. So what I want to do is I want to compute the low energy density matrix, right? What I was claiming to be the low energy density matrix. So what I want to do is in this expression for the density matrix, I want to do the partial trace over phi A bar, right? So the logic is going to be, I'll do that partial trace to derive the low energy density matrix, and you'll see the expression I've written down is related closely to the expression I would have written down for the Wilsonian effective action. Okay? That's what I'm going to try to argue to you.
So your label y is in momentum space or position space?
I haven't at the moment specified. In fact, most of the formulae I'm going to write down are going to be completely general. You pick your parameterization of the Hilbert space, right? Of the configuration space in this case, and split in whichever way you want. We will eventually pick y, A, and A bar to be low momenta and high momenta, but for the moment, it's just whatever label you choose to pick. Okay, so now I want to do the partial trace. So if I want to do the partial trace, I can write that as phi A, right? This is the partial trace, and that gives me the reduced density matrix. You can write that as 1 over the partition sum of, let's see, I need to do, I have d phi A of tau. And what do I need? I'm going to take phi A. This is the part that I'm not tracing over, minus beta over 2 is some phi A, and up there it's phi hat A. And then I'm going to put here an E, then I'm going to integrate over phi A bar. This is the part I'm tracing over. So because it's a trace, I'm going to put periodic boundary conditions on this part of the path integral, right? This has periodic boundary conditions. This has whatever initial and final configuration you want. That's what it means to take a partial trace times e to the minus s effective. Now, just look at this quantity, this integral times this. So that integral is exactly the thermal Wilsonian effective action. So let's write that out. You have e to the minus s thermal Wilsonian, right, is going to be equal to the integral from minus beta over 2 to beta over 2. Time runs over this duration of phi a bar. A bar is, remember, the part of the configuration space that we're going to trace over. Is going to be the UV degrees of freedom in a minute. So I do that integral, and I write down e to the minus se. That is the definition of the Wilsonian effective action. Right? Normally in the Wilsonian renormalization group, we're thinking of Euclidean momenta and integrating out momentum shells, but that's just a particular basis. Wilson would be happy to tell us to do this in whichever basis that we liked. We can pick whatever you want. Here I'm picking A and A bar, and you do this. This is the Wilsonian effective action for A, for the system A. So you can do some more massaging, and having done some more massaging, you can write this as follows. You can write this expression that we wrote down, this partial trace that we wrote down, is simply, so the density matrix for the part of the system that we're interested in is equal to 1 over the partition sum times the integral, where the field configuration goes from phi a to phi a hat d phi a of e to the minus s t Wilsonian. Okay, so that is our final formula that I want to look at. Okay, so some comments. One, I'm going to send beta to infinity, and this gives me the zero temperature zero temperature density matrix. So that is that object, as you send beta to infinity, is exactly the density matrix that we were interested in, right? So what this shows is that the density matrix, right, that this path integral sum, right, our density matrix, the one that we were interested in the low energy degrees of freedom, is simply the path integral over the Wilsonian effective action. Right, that's what you get. So that's comment 1. Comment 2 is I'm going to take the degrees of freedom to be p, or spatial momenta, and I'm going to take these things to be spatial momenta, not 4 momenta, as in the usual renormalization group, basically because I want to talk about states, right? To talk about states in the system, you need to have a time left over, and I've made the time Euclidean, and I'm playing games with it. So it's not usually in particle physics, we talk about integrating out entire 4 momentum shells and then continue back. Here I'm just going to integrate out spatial momenta, because that way I can directly talk about states and density matrices in this formalism. So that's one difference I wanted to mention. Now 3, another comment, is the Wilsonian action contains more information than the density matrix. I want to emphasize that. And that's because that's occasionally a source of confusion. The Wilsonian action is a functional of time-dependent field configurations, whereas the density matrix is a function only of the initial and final configurations. Right? So there's clearly less information in this. It's a little bit like saying the actual Hamiltonian of a system contains more information than just the ground state of the system. Right? If I tell you the ground state wave function, that doesn't necessarily specify the Hamiltonian uniquely. There's more stuff in the Hamiltonian than that. So, yeah?
I make a comment that there's this astonishing conjecture bouncing around in the condensed matter literature that what you said is not correct.
Yes.
That knowing the ground state of a local Hamiltonian is enough to determine everything.
So then that comes partly to my next comment. That partly comes to my next comment. Yes, that would be a beautiful fact if true. Yeah, and let's maybe it is. But that comes to my next comment. So usually we go from some exact UV Lagrangian action to a Hamiltonian, and we get some ground state, and then there's a question of whether specifying the ground state, maybe it's enough to specify the Hamiltonian, perhaps not. But this is because this is local Hamiltonian, which has a finite number of derivatives. SW, the Wilsonian action, has typically an infinite number of derivatives in space and time. Right? It's non-local, this action. Thus, you cannot associate a Hamiltonian and ground state canonically with it, right? Because it's got higher time derivatives. But it's a second derivative action that you can canonically associate with a Hamiltonian and a ground state. So what we've just shown is that what you can do is you can associate a density matrix in a canonical way with the Wilsonian effective action, right? So there's a that's the comment I wanted to make, and which has a bearing on what you just said, Dave. Right? It's not clear that the density matrix here contains the same amount of information. Probably doesn't. And in any case, you can't even go from the go to a Hamiltonian from this from the Wilsonian effective action because it's got an infinite number of higher derivatives.
I have a really naive question. Is it obvious that the Wilsonian effective action has acceleration terms rather than just kinetic phi dot
No,
power?
it's not obvious.
But you think it's true in general that it's phi double dot, phi
I
triple
think I think in general, there's no reason why it can't contain these. There's no selection rule that I know of.
It has everything.
Yeah, exactly. So David was asking, is it clear that it will contain acceleration, higher derivatives, etc. And there's no reason why it shouldn't. They may be.
It's we just usually separate them out from the norm.
I mean, there may be some special theory which, for some particular reason, is missing these terms. That's possible. But in general, there's no reason to you basically generate everything. Every operator that's there in the theory is generated, suppressed by some powers of scale. That's the usual Wilsonian setup.
Can I clarify? What's this claim that if you knew the ground state wave function, you knew the Hamiltonian?
It's too good to be true. If you have a local Hamiltonian,
Can't I just add anything to the Hamiltonian that annihilates the ground state, and that's a new Hamiltonian for which that's the ground state?
no, because any term that you add that's local will not annihilate the ground state.
Why? Oh, well, we can discuss later. Okay.
Yeah. I think the claim is that there's no counterexamples to this state.
Okay.
No counterexamples.
I thought obvious. I must be wrong.
That's an engineering proof. Well, so the fact that there's no counterexample to date means that in many interesting cases, it's nearly true in some way. So there's something interesting there, right?
I take the harmonic oscillator, a dagger a plus a half, and I add to it a dagger a dagger a.
No, it's trivially false in quantum mechanics. It's a statement in field theory where you add the local interactions requirement.
I mean, it's a little bit like the.
If I knew the ground state, I'd know the whole of the standard model Lagrangian up to the Planck scale.
Yeah.
Maybe.
Well,
There's a lot of information in the ground state. Right?
Yeah.
So
I mean, this is a version. This is the version of the can you hear the shape of a drum kind of
Yeah,
thing.
yeah,
You can know
yeah.
the spectrum of an operator.
But now you just
Then
enter the
but
ground.
now you only take one solution. You take a special solution. Right, exactly. There's a particular tone, right?
Listen really carefully to the
Yes,
lowest
there's a
tone.
particular pattern. Right. So, okay. Okay, anyway, that's not what I'm saying. So I'm going to continue. Right. So, all right. So I hope I've convinced you on general grounds that there is a relationship between the Wilsonian formalism and the presence of this low energy density matrix. Specifically, I would say that in the Wilsonian formalism, the way you compute correlation functions is you stick operators in here, inside the path integral. That's equivalent to putting the operator next to this and taking the trace. Right. So I would say that when you do calculations of correlation functions in the Wilsonian formalism, you are indeed computing the trace of the operator in the low energy density matrix. That, of course, raises the question, why haven't I noticed? And therefore, what we need to do is now actually carry out some examples of doing this kind of thing to get some sense for when it matters, when it doesn't matter, etc. And we also need to write down some measures of entanglement that we can use to determine, well, okay, fine, there's a density matrix, but how much entanglement was there in it anyway? So I'll just remind you rapidly of some measures of entanglement, and then our job is basically going to be to set up a little formalism, and then I'm going to carry out the calculations of this low energy density matrix and these various measures of entanglement in perturbation theory for phi to the n theories in d dimensions. Basically do the obvious to get some sense of what is going on here. So one measure of entanglement that you already know, which I'll remind you, is the entropy. So I have a system A, a system B, and I have the reduced density matrix A, and the entropy is minus trace rho A log rho A. This we're all familiar with. I will occasionally mention two other things, which are slightly more exotic for physicists, so I'll describe them a bit more. Suppose the Hilbert space factorizes into HA, HB, HC, which of course in the field theory, you have an infinitely many components like this, so you will surely have at least two. The lights are impressed with what I'm saying. Okay, so you can define a thing called the mutual information, which is a very useful quantity. And the mutual information between two things A and B is the entropy of A plus the entropy of B. So you calculate it from this entropy minus the entropy of A union B. And this is a quantity that is always bigger than or equal to 0, and it's only equal to 0 if the density matrix of the combined system is a product of the density matrices of the independent system. So it's a very sensitive measure of the degree of statistical independence and entanglement independence between, let's say, the degrees of freedom A and the degrees of freedom B. So it's a very useful kind of object to think about. Then there are similar generalizations, just like when you consider correlation functions. You know, there's correlation functions of degree 2, 3, 4, etc. There are cumulants. There are many such quantities, right? There are many such correlation quantities. In information theory, entropy is simply, if you like, the first order quantity. The mutual information is the second order quantity, and there are higher order quantities. I will write down one because it is useful. There's something called the triple information, A, B, C. So this is if you have 3 sets of degrees of freedom, then you have the triple information is the mutual information between A and A union B and C minus the mutual information between A and C and the mutual information between B and C. This is in fact symmetric between A, B, and C, even though the expression doesn't show that. It's in fact symmetric between them. And the use of this quantity is, you know how when you compute correlations between 3 variables, there is the connected correlation and the disconnected correlation. The thing you care about is the connected correlation, somehow an irreducible thing that requires 3 things. This thing measures something like that, except that this can be positive, 0, or negative in general in quantum mechanical systems. Okay, so these are 3 quantities that will be of interest to us. And now I just want to go ahead and compute all of these things in perturbation theory. Okay, so this is actually easy to do. Perturbation theory. And to make it as easy as possible to present on the blackboard, I'm not going to start with field theory. I'm going to start with doing quantum mechanics with 2 degrees of freedom. And you'll see the formula I write down will be trivial to generalize to field theories because you just have to add more indices to everything in town. So we're going to do it in that way. So I'm going to let the Hilbert space be, Hilbert space A times Hilbert space B, right? So this is not necessarily a spin. This can have many excitation states. Think about oscillators or something. And so the Hamiltonian, the free Hamiltonian, will take to be HA, the identity, plus 1 times HB. Namely, the free Hamiltonian acts independently, of course, in the 2 systems. I'm going to add a perturbation that mixes them to produce something interesting. And at the end of the day, we're going to take A to be low momentum degrees of freedom and B to be high momentum degrees of freedom. At the moment, they're just abstract. All right? So now the ground state is, we'll use the notation that this is 0, 0, which is 0 times 0. Okay, now I add interaction. Okay, and the interaction is H equals H naught, that is the bare Hamiltonian, plus some coupling times HAB. And of course, I'll take lambda to be small. And what I'm going to do is, since this is so trivial, I'm going to have a hand work out what is the new ground state in textbook first year quantum mechanics, and just work out the density matrix and work out everything in town, and then rewrite this in terms of field theory. So the new ground state, I'll call it omega, is, as we remember from our textbooks, it'll look like something like that. The old vacuum plus states where only the system A has been excited, plus states where only the system B has been excited, plus states where both have been excited. And n. And I need to normalize this. So I'll divide this by 1 over square root of n. And of course, n is basically the sum on A squared plus the sum on B squared plus the sum on C squared. Okay? So this is just the kind of formula that has to work out. And first order perturbation theory, we can work out what all of these coefficients should be. What's that? If this was a class, I would say, aha, people are awake. Okay. Right. Okay, excellent. So now I can just work out what the density matrix is, right? The density matrix for the whole system, rho is omega, omega. And rho A, the reduced density matrix, is the trace over B of omega, omega. And I'm going to cut a corner in view of the time and tell you the answer instead of working it out on the blackboard. And the answer, after you do some similarity transformations, which I'll tell you about later, after some similarity transforms, the answer turns out to be like this. It's 1 minus the absolute value of c squared, 0, 0, c dagger, where this is the matrix of Cnn, plus terms of order lambda cubed. Now you might look at this expression and say to yourself, what the hell happened to the A's and the B's? Or the A's and the B's? And so what you can convince yourself of is, well, first of all, A, B, and C are all of order lambda. But you can convince yourself that A and B only contribute to the entanglement entropy at higher orders, because it's only at order lambda squared in this expression that you know that this thing didn't come from a product. What do I mean by that? I mean how to put this. Yes, I know how to put this. A and B drop out because you could have an expression where omega is equal to the original vacuum plus some sum of A n n multiplied by some vacuum plus some term that looks like B n n. And then you could have here something that looks like C minus AB times a bunch of things. And you see this let me call this omega prime. This ansatz for a ground state would only have a non-zero entropy if this term is non-zero, because this is a product of states in system A and states in system B, right? So the difference between this expression, right? The difference between this expression and this expression at order lambda squared comes in this term. So all the entropy comes from this part, right? So the entropy will only get contributions from this part because this is a product wave function over here. And then here, this is of order lambda, the C is of order lambda, and this is of order lambda squared. Okay? So I'm now going to erase that and continue, because I want to write underneath that. So for this reason, A and B drop out, and only the C matters. So in other words, the only terms that matter are the ones that mix the systems A and B completely. You get excited states in both parts. And so you can work out from all of this that, let's see, the entropy is minus trace of rho log rho. And that's equal to minus lambda squared log lambda squared times the sum of AI plus additional terms, where AI are eigenvalues of CC dagger over lambda squared. So that's basically our final expression. All it remains to do is to plug in for C in terms of first order perturbation theory. That'll give us an answer in quantum mechanics in a two degree of freedom system. And then we'll immediately generalize that to quantum field theory. And then we can just basically write down the answers for a whole bunch of field theories. Okay, so that's the answer. And okay, so that's the answer. And in first order perturbation theory, you have C and N equal lambda times, here's the excited states, HAB. This is the interaction Hamiltonian. Here's the original ground state. You square it, and there are the usual energy denominators, E naught plus E naught tilde minus En minus En. Okay? So that's the answer. So let's write down what you get. You get SA equals minus lambda squared log lambda squared. That's the entanglement entropy in this 2-degree of freedom system. Over sum, and you have to do a sum over states where both systems A and B are excited of N. Sorry, this wasn't squared, and this wasn't squared. But here it is. You have absolute value N, the interaction Hamiltonian, the ground state squared divided by the energy denominator E naught tilde minus En tilde squared. Okay, so that's the answer. So this is the general answer for any division of a system. If you divide a quantum system into 2 parts, A and B, this is the general answer for the entanglement entropy in perturbation theory of system A if you have an interaction Hamiltonian AB. So that's the full answer for us. Okay. Now, in a similar way, you can compute the mutual information, and you can compute the triple information. I won't do that for you in the blackboard. I'll just mention to you a result that comes out of this that's worth keeping in mind. There was a paper by Hayden, Maloney, and who was the third person? Hayden, Maloney, and third person?
Part of the triple information.
Yes. What was the third author? It's always good to blame Witten for everything, but thank you, Hedrick. Same thing as Witten. Right. So it is lovely. So Matt, so Hedrick, Maloney, and Hayden had a result where they showed that in ADS-CFT, this quantity, using the Takayanagi formula for entanglement entropy, is always positive. They have a particular sign. This formula, you can derive from this formula for the triple information that in any perturbative expansion, the triple information always has the opposite sign. So that's a guarantee. Right? So our results show that. And so it shows that whatever result, if you believe the Takayanagi formula and the results of these other 3 folks, that you have just, it is a fact you cannot get that from perturbation theory, or from first order perturbation theory, anyway. Okay, so that's a fact that I would like to mention. Okay, so now let's see how you're supposed to apply this to quantum field theory.
That went very fast. You show that the triple information always has the opposite sign from what?
Okay, this we show that in first order perturbation theory, in this way, we show that I, A, B, C is always less than or equal to 0 in perturbation, in first order perturbation. For any, in any way you cut it, for any set of degrees of freedom, in whichever way you do it, you will always get this. And in ADS-CFT, using spatial entanglement entropy, Hedrick, Maloney, and Hayden showed that I, A, B, C is strictly positive. So there's a direct, so you just cannot reproduce the usual ADS-CFT thing from standard perturbation theory. That's an aside I'd like to mention, because somehow I have a feeling it'll come back someday, or it'll be useful for something at some point. Okay, so you can derive many results like that about the nature of these entanglement entropies in perturbation theory, and they are useful.
Is that a strict greater than?
What's that? Yeah.
ADS-CFT is strictly greater than?
I think they found it was positive. For us, it's strictly less than.
I'm saying, could they get 0?
I don't think they can get 0.
Is that what seems to suggest that there's no ADS dual to a free system?
Maybe there isn't.
But this is a very generic kind of system, right? So what, you haven't made any particular assumption
No.
about your system?
No. This is first order perturbation theory, right?
But
Oh, yeah, but free.
But also, isn't it that, the next order would not change the sign of something if it's,
It could,
be a small.
but in free theory, there's no next order, right? That's what he's going. Can we come back to this? I think it's actually interesting. That's why I mentioned it.
Yeah, yes.
But I'd like to come back to it at the end because
Yeah,
I'd like to say a couple more things.
I'm going to start shaking his signs soon.
Yeah, I've been ignoring the signs so far.
Wow.
Well, oh, good, excellent. I haven't looked at you, so I wouldn't know if it if it'd come up. And there's a reason I'm not looking at you. Right. So in quantum field theory, the way you can generalize this to just deal with quantum field theory in general is we started here with system A and A bar. Now I'm going to take A and A bar to involve, a whole bunch of momentum modes, if you like, and another whole bunch of momentum modes. So basically, I'm going to take this as Fock space labels. And if I take A and A bar to really be Fock space labels, I can basically take this formula and rewrite it instantaneously. Specifically, after you do a little bit of work, you could write down the following. So consider scalar field theories. Scalar theories of the following form. I'll write down the action to be dd plus 1x, 1/2 a standard kinetic term, minus 1/2 m squared phi squared, minus lambda over n factorial, phi to the n. And I'm going to take phi, the field, to be some coefficients times the sum of a e to the minus ipx plus a dagger e to the plus ip dot x. There's some normalization, one of the square roots of omegas and stuff, the standard canonical expansion of a field. And then you can do some work and show that there's the following expression for the entanglement entropy density at the end of the day. So here what I'm going to do is I'm going to imagine that I have here is the momentum, and here is mu, the cutoff. So I want the entanglement entropy between momenta which are less than mu and momenta here which are bigger than mu. Okay? That's the basic kind of quantity between the infrared, if you like, and the UV. So the answer turns out to be an expression that looks like minus lambda squared log lambda squared, some numbers which we don't have to care about, times a particular integral over some particular set of momenta. I'll explain what this mu here means in a second. A product over all of these momenta, ddpi. There's some momentum conserving delta functions, and then a bunch of energy denominators. Omega 1 through omega n, omega 1 plus going to omega n some squared. This is for phi to the n theories. Okay? So this is an integral. I won't write out the details, but this is an integral in which you insist that at least one of the momenta is lower than mu, and one of the momenta is higher than mu. That's because in this sum, remember, you needed here, excitations both in the system A and in the system A bar. You need excitations in both systems to contribute to leading order to the entanglement entropy. That manifests itself here in requiring that at least one of the momenta be below the cutoff and one of the momenta be above the cutoff. This is our final answer. And now it's tedious, but pedestrian to evaluate this in various cases. So what I'm going to do is simply write down the answer of doing these various integrals in various cases, and you'll see some interesting things develop. Okay, so let's write down some results. So I'm going to write down, for example, phi cubed theories. So in 1 plus 1 dimensions, it turns out that S of mu is proportional to mu over n to the 4th for mu much, much less than m, and the cutoff is less than the mass. This is the kind of thing you were talking about. As you can see, as you make the cutoff small compared to the mass, there's no entanglement because basically the particles are going away. They're not really propagating. Interestingly, at the other end, you also get something that goes to 1 over mu cubed when mu is much, much bigger than mass. I'm leaving out dimension-full factors and everything, so I'm not trying to get things to look right here. Okay? So you can similarly do in 2 plus 1, etc. You get in 2 plus 1 phi cubed and 2 plus 1, you get S of mu is proportional to 1 over mu when mu is much, much bigger than n, etc. Okay? So you can, and then you can do phi to the n theory. So what I'm going to do is I'll write down the general answer and then try to reason as to why you're getting that answer. Instead of setting out each case, I just wrote this down to assure you, you can just do this in a practical way. Just do the stupid integral one way or the other, and you will get an answer. So the answer,
The very stupid question is mu goes to infinity. Do I always expect 0?
no, not necessarily. Right? That depends upon what's happening with the coupling, how many degrees of freedom. There are divergences here because for very high dimension, you may be getting many, many degrees of freedom, and so the rate of fall off of the coupling, the effect of coupling, may not compete sufficiently well with the growth of the number of degrees of freedom.
It's renormalizable, maybe.
Yes, yes, exactly. So depending upon whether the theory has decoupling, whether it's renormalizable, so different classes of theories are going to have different properties in this quantity. That just hasn't been explored, right? But it's clear that they will have some different kinds of properties based upon what, the rate of the rates at which the degrees of freedom grow versus the coupling, because clearly those are the two things that matter. And we'll see that explicitly in a second. So if you evaluate this quantity, what you find is the answer goes like 1 over, this is for mu much, much bigger than the masses. It looks like 1 over mu to the dimension. So this is mu much, much bigger than masses. This is phi to the n theories in d plus 1 dimensions. You get 1 over mu to the d plus n minus n times d minus 1. And you can write this in a suggestive way. This is mu to the d, and I'll explain why that's interesting in a second, times a quantity squared. This quantity is 1 over mu to the d plus 1 minus n d minus 1 over 2. That may look obscure, but it isn't. First of all, this is the rate of growth of the number of degrees of freedom in the system with mu, right? I'll be done in 5 minutes. Thanks. So this is the rate of growth of the number of degrees of freedom. So that's clearly one thing that's somehow appearing. And here, the pertinent thing to remember is that if you have a coupling for phi to the n in d dimensions, then the dimension of that is 1 over length to the power d plus 1 minus n d minus 1 over 2. And everywhere, there's been a coupling squared appearing, right? And that is that coupling squared. So I should say, in addition, there are logs here. And the logs, of course, that's often where a lot of the fun is, in the logs. I'm not going to talk about the logs, right? So here, the basic scaling of this quantity clearly matches our expectations based on the running of the coupling and the rate of growth of the degrees of freedom, which then is related to the comment that you made. So I want to finish by discussing one further thing. So where is this coming from, right? The place where this is coming from is when you try to do these integrals for this entanglement entropy, right? The two things that matter are, well, there's some momentum-conserving delta function floating around, but there's some integrals over momenta. So phase space matters, the number of degrees of freedom matters, obviously. Of course, the phi to the n, what interaction you have obviously matters. That's the delta function. And then there are these energy denominators. Now, these energy denominators in phase space are exactly the two things that come in demonstrating that theories are renormalizable or satisfy decoupling and doing the renormalization group analyses of things. It's these things that at a practical level come into any calculation of a Feynman diagram. And so it's the same physics, in a sense, that's giving rise to this change in the entropy. So it's worth asking, what is the relationship between what we have said and more conventional understandings of something like decoupling, right? It's worth asking that a little bit more. So that's what I'll finish with in a minute. 1 minute. Yeah, it'll be 3 minutes. I'll run 2 minutes over. I'm sorry. Is that possible? Time warp. It's 2 minutes ago. I'm going to finish in 1. Okay. All right. So these are all theories. So you might imagine that what's driving at least the results of phi to the n theories that we're talking about is something like this. So you have a scale mu, and you expect that there's some sort of skin of entanglement around the scale mu, and you might expect that well above and well below the modes aren't entangled. So it's really what's going on is somehow near the scale mu. So of course, how the coupling changes with scale mu matters, and the number of degrees of freedom at scale mu matters, right? This would explain why this kind of thing is happening. So there are many ways of trying to analyze this, and I'll tell you the easiest way, because it's also the quickest way, And we can do it quickly in the remaining time. So I want to study something about the range of entanglement. And the way I'm going to do it is I'm going to consider, here's the range of momenta. Here's the momentum P with a little volume dQp around it. Right, this is in 4 dimensions, say. Or let's say ddp, I don't know. Here's the momentum Q with a volume ddq around it. And I'm going to ask the question about, I would like to know the quantity IPQ. I defined earlier on a quantity called the mutual information. There was some complicated definition in terms of the entropies. But remember, the meaning of mutual information between P and Q is how much, well, if I was an information theorist, what I would be saying is that IPQ tells you how much information in bits, knowledge of the state of P gives you about the state of Q. Right? It's in a very practical way telling you how correlated the state of the field with momentum P is with the state of the field and momentum Q. It's a sensitive measure of that. That's, of course, the kind of thing we're interested in, right? We want to know how much this tells you about this. This should tell you nothing about this. Okay, so let's see. So you can write down a formula, which I won't derive, because there's no time. And it looks like some integral over momenta times the product from I equals 3 to n ddpi of some delta function over momenta, and again, some energy denominators and so on. Okay, I just wrote this down for protective coloration to show you we did some work. I'm now going to specialize to one case where we can write down the answer without doing an integral. So notice that, actually maybe I should explain why I'm going to do the special case. So this thing here, this momentum conserving delta function has a P plus Q plus P3 to Pn in it. So this is n, so this is a phi to the n theories. So notice that if I have a phi cubed theory, right, then I have a P, a Q, and a P3, and everything else is gone, which means P3, the third momentum which I've got to integrate over, is determined by the momentum conserving delta function, so I don't have an integral to do. So for that reason, for simplicity in this talk, I'm going to pick phi cubed theories because they're easy for me to write down on the blackboard without dealing with integral. Okay? So let me therefore consider phi cubed theories. And the answer turns out to be, for phi cubed theories, the mutual information goes to minus lambda squared log lambda squared divided by 1 over omega p, omega q. So that's the energies of these two modes. Omega p plus q, you add up the momenta, and then you get omega p plus omega q plus divided by omega p plus q squared. So there's a lot of structure in this, but one thing is for sure is that for fixed p, this mutual information is proportional to 1 over q to the 4th for large q, which means as they separate a lot, right, this thing in fact falls off with some kind of power law. There's other things going on too. When any of these things vanish, this thing, the mutual information grows, and we could discuss why that's the case.
That's dimension independent, or that's particular to 4 dimensions?
This is a dimension independent statement. This is a dimension independent statement, which is also surprising that you can make a statement like that independent of dimensions.
So for example, it's true in 8-dimensional field theory where it's not renormalizable?
Apparently. Remember, this is perturbation theory, first order perturbation theory. So there'll be other issues that come up as to whether or not you can validly use perturbation theory and stuff like that. Right? If you add higher orders, does it resum? Anyway, so I'm going to end there because this tells you, I mean, as you can see, the expected power law drop-off is sort of happening here. This is far from a done deal. As far as we're concerned, I think we've just plumbed, I think, what an interesting quantity to look at that people haven't looked at before. And there's a lot of physics hidden in it. You can study how different subsets of momenta are entangled in different ways, and they reveal different things about the nature of field theories. Personally, I'm very interested in the question of if you had a non-commutative field theory where you don't have UVIR decoupling, you know, with the star product and stuff like that, space-time non-commutative. These things will give different results from standard field theories, I expect. It'll be cool to do that. There are lots of integrable flows and supersymmetric field theories where there are interesting flows where one could try to shed light on this. As I mentioned at the very beginning, when I gave my conclusion, it would be cool to see whether this kind of notion of entanglement between UV and IR degrees of freedom has any bearing on the geometry of surfaces in ADS that don't touch the boundary, following on from the Takayanagi idea. And finally, I do think that these kinds of ideas have a direct bearing on the analysis of the complicated wave functions, multi-scale entangled wave functions in condensed matter physics. Those folks, they have two interesting techniques, one called the density matrix renormalization group, and the other one is called the multi-scale entanglement renormalization ansatz, DMRG and MERA, which are techniques to try to deal with these kinds of long-range entanglements in numerical ways. I believe we're giving a different perspective of the subjects, which I think is useful. I'll stop there.
Okay.